Hello, everybody. My name is Battista Biggio, and I'm here today. I'm assistant professor at the University of Cagliari in Italy, and I'm here today to tell you about the story that led myself, together with Blaine Nelson and Pavel Laskov, to write this paper 10 years ago, which is poisoning attacks against supervector machines. So a little bit of context is that I'm not going to tell you the same story I told 10 years ago in Edinburgh at ICML 2012. If you're interested, you can check out the video on YouTube by yourself. What I want to discuss today is something different, and is somehow the story behind the paper and how we got to work on that. So where did it start from? I was actually finishing my PhD in Cagliari in 2010, working with Professor Fabio Roli and Giorgio Fumera, who were the former supervisors for me. And it was actually their idea to invite me to go abroad and meet Pavel Laskov in Tübingen. He was actually a professor there for a time, and it was kind of the perfect storm, because there I met also Blaine Nelson, which was moving from UC Berkeley after his PhD. And let's say it was quite nice to work with both of them, and where I and Blaine were actually both postdoc researchers there visiting Pavel's group. So a little bit of context about poisoning attacks back in the early days, so around 2006 and 2010. That at that time, mostly the attacks were focusing on simple models, which were somewhat easier to understand and for which you can have some kind of tractable derivations, like centroid-based anomaly detection and linear models. But it was especially done in the context of security-related applications, including spam filtering, network intrusion detection, and warm signature generation. So the goal of the poisoning attack in this case is actually to inject training points to compromise classification of clean test points. So in the case of spam emails, you can see that as the attacker is more able to control kind of fraction of your training set, up to 10% in this case, you see that more and more legitimate emails, which are not under the control of the attacker, are misclassified as spam. So the idea is to create a sort of denial of service for the system. So that was like the main idea behind these poisoning attacks in the early days. And then when I met Pavel in Tübingen in 2011, his idea was to showcase if these attacks were possible, but against a more complex classifier, a more popular one, and maybe something which was closer to the state of the art of algorithms actually used in practice. So we decided to start from analyzing the supervector machines, because they were not only quite popular at the moment, but they are also theoretically grounded. So the thing we had in mind is that probably we can find something optimal to kind of destroy the performance of this classifier. And frankly speaking, I had a bit of a hard time in bootstrapping with supervector machines, because I was not so familiar with them at that time. So I had to go back to the basics and study these nice let's say the Bibles of supervector machines from Nello Cristianini and John Shaw Taylor. And so I started from learning about the leave one out bounds and incremental learning, all things that have somewhat a relationship in trying to understand what happens when you add a new training point to the supervector machine and how the solution changes. In particular, this initial paper by Kovenbergs and Tommaso Poggio was like the first milestone that I had to study and understand well before developing or coming up with the idea of poisoning the SVMs. In this paper, what the authors wanted to do is like update the solution of the SVM when points are added one at a time or removed one at a time. So you want to actually find the same optimal solution when you have your original training set plus the new point, but without retraining from scratch. That was the idea. And the main trick that they used is like this idea of adiabatic increments, so that you can add the new point to your supervector machine and you start learning it, which means if it's already correctly classified within the margin, it's a so-called reserve vector. The final dual coefficient for this point will be 0, so you actually have to do nothing in this case. But if the point is going to be learned either as a margin support vector or as an error vector. So the alpha value corresponding to it will be positive. Then what you need to do is actually learn this point. And the idea was that you can learn this point gradually without perturbing the current solution of the SVM, which means by retaining optimality of the whole solution as you gradually increase the value alpha C for this specific point. As you see from the picture, what happens is that actually under the assumption that the three sets of vectors that you have, which are mostly the one that you see here, so you have either a reserve vector, a margin support vector, or an error vector, this current kinds of set remains constant, so remains stable, and based on this assumption, you can actually understand how to update the SVM parameters like alpha and bias, so the dual coefficients and the bias, and you can update these, by retaining optimality of the solution and incorporating the point to the learning process. As you see, the solution is piecewise linear, so you can update the point in the parameters in a linear manner as you increase alpha C, but at some point, the structure of your SVM solution will change. So the three sets of points will change, and you need to update this current set. But it was quite efficient and instructive to look at this paper to start with. However, our problem is a bit different and was a bit different because we wanted to find kind of the worst training point that once learned by the classifier screws up the classification on legitimate and clean test data. So just to exemplify this, if you consider a linear SVM trained on two classes, you find your nice maximum margin separator, and now you can measure the error on a clean test set, which is something like 2% in this example. If you add, let's say, a red point over here, then what happens is that the boundary kind of tilts a little bit counterclockwise, and you see that the classification of the clean data changes. Okay, so not only on the clean training points, but also on a separate clean validation set where you measure the test error actually. But now the question is, and in this case you go up to 4% error. The question, however, is where should I place XC labeled as red such that the classification error is maximized, because that's the goal of poisoning actually a classifier. And then in this simple case with two features, with a 2D feature space, you can actually exhaustively inspect the objective function. So you can add XC to every possible location of the space, retrain your model to learn the poisoning point, and then actually measure the classification error on a separate test set and plot the current value of the error in colors. And then you have your nice objective function sketched here, and you see that the optimal location of the point is actually bottom right here in the plot where you see red, where the maximum classification error can be achieved. So that was kind of what we wanted to reach. And the main idea was actually to start from the incremental learning paper, but we're not interested in adding, a point. So the goal is not to learn a new point, but is actually assuming that you have already learned a point, how to change it, how to shift it in the feature space so that the performance of the classifier is decreased on the other clean points. Okay, and in this case, if you look at the solution, well, the solution is not piecewise linear anymore, so you cannot work on finite differences as Kovenbergs and Poggio were doing, but you have actually to use gradients. So this was the first ingredient that we put in, and then the goal was to compute this derivative of G with respect to the training point, to the poisoning point, where G is the score that the SVM assigns to the clean points. Okay, well, you can actually differentiate this in a similar way to what Kovenbergs and Poggio did, but now the challenge is how, and you see what you have in these terms here, the derivative of the coefficients alpha with respect to the training points and of the bias as well. So in other words, this means that to solve this, to compute this gradient in closed form, you need to understand how the solution of the SVM changes while you shift your training point in the feature space. And again, looking at the original paper, we can work under the same assumption, namely that you preserve optimality of the solution so that you keep the Karush-Kuhn-Tucker condition satisfied. For the SVM, as I said before, this means that the three sets of vectors that you can have, like the margin vectors, the reserve vector, and the error vectors, stays the same. Now, under this assumption, which clearly holds if you just do an infinitesimal update, because you are like working with gradients under the assumption that this solution will be smooth somehow, you can actually, let's say, use these KKT conditions are just a set of linear equations. So you can invert them, you can solve the linear system, and now you get the closed form expressions for these gradients that you need. You can plug them back onto the derivative of g with respect to xg. So now you know that if you shift, the training point in the feature space, your poisoning point in feature space, the score of the other points will be affected according to this derivative, right? And then we just need to connect the last piece of information, which is now, how do I have to change these scores such that the loss is maximized? And then you can finally formalize an optimization problem where you actually want to maximize the loss on the clean points by playing with xc, so by shifting the point in the feature space. And then you just can solve this by gradient ascent. So you take the derivative that we have, chain it with the derivative of the loss, and then you're ready to run the algorithm, which is exemplified in these 2D cases. Basically, what you do is you start flipping the label of, you clone a point in a class, you flip the label. So now you start from this x0 red point, and then you follow the gradient up to the local optimum. This worked for linear subprofessor machines, and of course also for kernelized versions, like using the RBF kernel. The only thing that you need is that the kernel is basically differentiable as well. Of course, we had some experiments also on some less toy data, even if it's just mnist digits. Here, we trained a subprofessor machine to separate force against zeros, and we use just 100 points just for the sake of showcasing the attack. What happens is that if you just take this digit 4 and you flip the label, nothing really changes in terms of the classification error. But then if you optimize the feature values according to our attack, what you end up is having this kind of blurred digit, which is a 4 resembling a 0 in the background. And then you see that with this point, the testing error reaches up. Learning this point causes the testing error to go up to 20% by just adding a single point. So 1 out of 100 points, which was quite surprising at that time. And then only a couple of years later, in 2015, May and Zhu actually find a much more elegant way to formalize this problem in terms of a bi-level programming problem, where you actually want to maximize the validation loss on clean data. And on top here, you have no attack points involved with respect to the training point xc, which is only appearing in the inner optimization problem, which is actually just learning the model, including the poisoning point. Okay, so that's the actual formalization of poisoning attacks. And this can be solved exactly as we did. So you can replace the inner optimization problem with its equilibrium conditions, so the set of linear equations for the KKT from the KKT conditions, and then you can actually compute the hypergradient in this case if you want, because this is actually the same thing of doing hypergradient based optimization to estimate the hyperparameters of a model, or even to do some kind of meta learning things and so on. So it's the same bi-level problem that you have also under these other problems. Now, just a little bit of understanding why and when this attack actually works. And first, it was very effective against SVMs because they have this hinge loss, which is unbounded, and because convexity, this is implied by convexity essentially. And based on that, if the feature space is also not bounded, ideally you could take one training point, send it to infinity. This would have infinite loss, and so it will affect all the classification of the other points, of the clean ones. So you can basically arbitrarily decide which kind of linear classifier you want to end up with. Of course, these attacks to work also requires that the model has somehow a low capacity, or it is quite constrained, like a linear model or some other strongly regularized models, because otherwise, if you add points which are farther away from the other ones, from the rest of the training set, they will be just classified almost independently from what happens in the other areas of the feature space. So this attack indeed is not really effective against over-parameterized models and deep neural networks. But you have other versions of poisoning that you can actually do on them. Now, a very important point is that these kinds of attack, where the attacker is assumed to control a very small fraction of poisoning of the training set, poison it to cause generalized, misclassification errors on all the other points, is relatively easy to detect, or it's in other ways we have effective defenses against it. The reason is that the poisoning point to work actually has to show some very outlying behavior with the rest of the training data, and this makes it easy to detect. Conversely, if the poisoning points are quite in the distribution, then you would need a lot of points to drift the model. So let's say if you want to poison realistically a model with 2-3% or up to 10% of points, they have to be quite different, and so they are detectable. So you always have this tension between detectability of the attack and actual impact of the attack on the classifier. To detect them, you can just resort to some robust learning techniques or data sanitization. Okay, that's the kind of defenses that work against them. So far, let me recap a bit. The poisoning attack we proposed in 2011, 2012 has been, let's say, the first gradient-based attack on machine learning, at least to the best of my knowledge, where we are attacking, some more complicated learning algorithm. And the key idea that we had at that time was that formalizing the attack as an optimization problem was the essence behind, showing the optimal attack against it. Sorry. So, based on the same idea, 1 year later, we thought, why we just don't solve an easier problem, which namely is that of evading a trained classifier, right? And then this was fairly easy to kind of write down, because then the classifier is trained and we have a data point X, and we just want to cause a misclassification by manipulating X. For example, you have your spam email and you want to have it misclassified as legitimate by just changing some of the words in the text. Of course, all this problem makes sense only in applications where the manipulation is somewhat bounded, like because for spam, you don't want to destroy the actual message for a human. You want that the human still understands the message. And for malware detection, for example, you want that the exploit remains executable so that the malware actually preserves its functionality. In some cases, this can be formalized very with some easy tractable mathematical, let's say, constraint, which is LP norms. So, for instance, if you bound like this distance in the L1 norm for a spam email, it means that you can basically manipulate up to epsilon words in the text or something like that. And now that the problem is formalized, it's actually nice to see that you can solve it with, it's a nonlinear constraint optimization problem, so you can actually solve it with standard gradient descent algorithms. You basically compute the gradient of the objective, assuming that the classifier is differentiable. You follow this direction. When you hit the constraint, you just project the point back onto the constraints. And this can be done very easily if the projection is convex. The nice thing is that many of the classifiers that we work with are actually differentiable, like subprofector machines and neural networks, because you need the same property for training them. So ironically, you can fool these models by just using gradient descent again, which is the workhorse tool for actually building them. And of course, we had another example on Android 10 digits. So we took again, I think, a nonlinear classifier here. It was 3 against 7 this time. And then we optimized the attack against this model to have a 3 misclassified as a 7. And what you see here is that actually a few modifications were enough to evade detection. So this was back in time. This was 2013. And after that, Christian Szegedy, Jan Goodfellow, and other guys from Google Brain, they, discover essentially the same effect on deep models, on deep neural networks. And so we had this discovery of adversarial examples 1 year after our work in 2013 and 14. The nice story, which is maybe less known about this, is that they came to derive these adversarial perturbations by, computing the gradients of the model, basically, but coming from a different angle. So they wanted to actually investigate model interpretability. So starting from this image of the school bus, they wanted to see when it becomes misclassified as an ostrich. so they were expecting to see some feather or wings in this kind of morphing process from the school bus to the ostrich. What instead they found was, quite surprisingly, that only these small, almost imperceptible perturbations needed to be applied to the original image to have the misclassification there. And so, let's say, coming from the interpretability angle, they discovered actually the same phenomenon, right? That you can fool models by looking at their gradients in input space. Of course, this work had, let's say, much more impact than ours, because they were really fooling models that to some extent claim to be, to have superhuman performance. So this was kind of shocking for the community. And since then, machine learning security as a field boomed. So if you look at this page, which is maintained by Nicola Scarlini, you see that up to 2022, we have more than 5,000 papers only on adversarial examples. And I think there are other 5K, at least, for other attacks. So security of machine learning was really becoming, really became an hot topic. And many other attacks, other than evasion and indiscriminate poisoning attacks, arose. So you have here a categorization of them, which I'm not going through, but if you're interested, you can check this wild patterns paper that I co-authored with Fabio Roli back in 2018, where we kind of categorize all of them using a, let's say, quite general threat modeling technique. And again, in the same paper, I tried to kind of reconvene, the papers that were done before deep learning came to be an issue, and adversarial examples were discovered, with actual literature on the security of deep models. So trying to establish, connections and what has sort of being rediscovered over and over in the other communities. I have to say that there is also a nice book on adversarial machine learning by Blaine Nelson, Anthony Joseph, Doug Tiger, which is titled Adversarial Machine Learning, and summarizes basically all the results that we were aware of before actually the phenomenon, the discovery of adversarial examples. And I mean, there are several things which have just been, to some extent, renamed and reused, but they were also studied with more interesting, also from the theoretical perspective. For example, adversarial training is one of them, right? There was work by Tobias Scheffer and Michael Bruckner before actually Goodfellow invented adversarial training they were studying game theoretical models for classifiers versus the adversary. So I mean, a lot of work is already there. There is the zero-sum games, which is actually the adversarial training formulation. There is non-zero-sum games with imperfect knowledge of the players, and so on and so forth. And you have mathematical guarantees to find like the Nash equilibrium, if it is unique, when it exists, and so on and so forth. So my invitation here for people that are working in this field is just to go a bit deeper and search also for other work which was done prior to deep learning that has some real and actual value there is value in learning that is what I mean. So what happened to poisoning in the last 10 years now, since we started with this paper and all this adversarial example work came out? Well, luckily for this, we have a new survey which was just published on arXiv a couple of months ago. And if you see, after the early work on indiscriminate poisoning attack, there was this kind of line continuing here. This is using the same threat model we used back in 2012, so that you can inject only a few points that could be potentially largely different from the rest of the training set. This is one line of research where I think the threat model is more realistic also for practical applications. And then there is another line stemming from here, which is more about a slightly different threat model, where the authors consider changing the whole training set, but with a smaller perturbation. Okay, so there is a perturbation budget on each point. And there is work also on deep neural networks against these kind of poisoning attacks. But frankly speaking, I don't see any realistic applications where this applies. Not to my knowledge. Maybe and in fact, they are published mostly on machine learning conferences and not in computer security ones. There are two. So another thing I want to say here is that these kinds of attack can be somewhat defended. So we have defenses against them that work quite well. And there are other attacks which are more complex to be detected because they just poison the model, but to cause specific misclassification at test time. So you don't want to create errors on the whole test set, but you just want to focus on, let's say, specific points or specific classes or subset of classes. This is what is called targeted poisoning attacks. Backdoor poisoning is slightly different, but it actually works with the same rationale that you target specific points. In this case, they have to include a specific trigger that only the attacker knows and knows how to activate it. But more or less from the, let's say, from the technical viewpoint, they are pretty much the same thing. And this is much more complicated to understand and to defend against. All right, so let me move to the concluding remarks, in a sense, where it's been a long time now that the community is questioning somehow if these attacks are relevant in practice. Okay, there are some studies where the authors invite some people from companies to respond to some surveys to get an idea of what's the level of knowledge that they have about machine learning security, what the most relevant attacks are. And there is sort of agreement that poisoning is one of the most relevant threats, and model stealing could be something relevant if you are scared about the fact that someone may steal your intellectual property, so your model, and sell maybe the same service at a lower price. However, I have to say that most of the attacks that we optimize and we come up with in the machine learning community are not really having an impact in practice. If you look at the practical attacks that have real-world impact and that somehow target a machine learning system or a model, they are actually not exploiting gradients or fancy optimization techniques. For example, in this paper, the Dolphin attack paper, I think it was a CCS 2017 paper, what the authors did was just basically fooling the microphone that you have on your devices, either mobile phones, Siri, Alexa, whatever. And the idea was that they wanted to craft an inaudible signal, an inaudible audio signal to the human, but by exploiting the nonlinearity of the microphone, they were able to bring back to this inaudible signal from the ultrasound frequency back to the audible range. So it was actually after the microphone, it was shifted in frequency, and then your mobile phone or device actually executes the command. And this is a super cool paper, and they end up, as a concrete result, the new microphones that we have in the new phones and in these new devices are actually fixed to deal with this potential issue. And this was not attacking, the machine learning model at all. So there was no gradient and nothing like that, but they were just exploiting, let's say, a pre-processing failure in a sense. So after more than 10,000 papers on machine learning security, we have clear evidences that any model can be pretty much attacked in vitro, so in a laboratory setting. And that we know also that the strongest attacks are very hard to be defended against in vitro. So adversarial examples are kind of inevitable in many cases, for instance. However, we still don't know if and when such attacks are feasible and work in vivo, so in real-world application, which means against real systems and in real operational conditions. And we don't even know if we need defenses in these cases and how to develop defenses which are, the practical ones that are best suited to this specific application. So there is a kind of debating issue at this point, whether these attacks are becoming more and more an academic game, or at least they're just useful to understand how to mimic maybe the human vision system to some extent. But it's not clear if you approach them from a security angle, if they will ever become a real threat in practice. And then the question is, if no evidence of these, that these attacks will be effective against real systems based on machine learning deployed in real operational conditions, so if this is remaining unclear, what will be the future of all this area, of all these defenses, or this area of adversarial machine learning as a research field? It's unclear to me at the moment, but I like to ask a question and challenge the audience as well. What I like to do is thinking in the so-called Pasteur's quadrant. So Let's look at practical problems like from industry, which request for some more fundamental and basic understanding, because those are the challenging problems that may have, if we solve them, they may have real practical impact. So what I'm advocating here is like, if we can use some of the techniques from machine learning security or adversarial training, for example, if some of these things can be helpful to solve some of today's industrial challenges, not necessarily strictly related to the fact that you want to detect attacks or things. For example, will any of these techniques be useful to improve robustness or accuracy over time? For example, requiring less frequent retraining rounds when you have these systems that are, constantly deployed, maybe in machine learning operation chains or pipelines. Would any of these techniques help in improving out of distribution detection and provide, reliable predictions, so confidence values in agreement about how far your point is from your training data or something like that? Will any of these help to improve maintainability and interpretability of the deployed models, like simplifying the update procedures, or even to learn more reliably from noisy and incomplete labeled data set? Because this is like a very challenging problem in computer security. So with that said, will we be able to build more reliable and practical machine learning models using machine learning security or adversarial machine learning? Or in 5 years from now, will this just remain a ton of papers that we wrote, but it's not really impactful in practice? That's my provocative question to the audience and to the community. So let me conclude by, first of all, apologizing for not being able to participate in person to this meeting. I would really have loved to join you and have engaging discussion with you all. But with such a short notice, it was quite complex to me to reschedule all the trips that I had already planned. And so, unfortunately, I was just recording the presentation. And second, I want to thank the committee of ICML to have given the award to us. I'm honored and humbled to receive it. And I think I can speak in the name of Pavel and Blaine, and they will do that. They just acknowledge the same fact. I also would like to thank all of my collaborators, people who I worked with across the years, because, if I'm standing here today, it's also thanks to you. So thanks a lot, and hope to see you soon.